Hi everyone. So in this video, we're going to be talking about how we can use exponential functions to model different types of real-world situations. So I want to say up front that this is a really big topic and we're just not going to be able to get too deeply into it in this one video. So this video is going to be kind of an introduction and some examples. But if you find this stuff interesting, I would encourage you to take a look at section 4.7 in the book. You'll see that there are some concepts and some examples in that section that we're not going to get to. Okay, so before we get into, like I said, modeling some real-world situations, I want to start with an example that isn't super realistic, but I think will help you kind of understand what makes exponential functions exponential functions. So let's say that you are lucky enough to win a contest. And so you have two different choices for what your prize will be for this contest. So the way that these prizes work is that you're going to have an account opened. And in the first choice, if you choose the first prize, into that account, $1,000 will be deposited every day for a month. So $1,000 on the first day, another $1,000 on the second day, and they'll keep depositing $1,000 over and over. So in the second example, rather than having the same amount deposited each day, what's going to happen is that you're going to get 1 penny, so 1 cent deposited into the account on the first day. And then each following day, what will happen is that the amount of money in the account will double. So on the first day, you'll have 1 cent. On the second day, you'll have 2 cents. On the third day, you'll have 4 cents. On the fourth day, you'll have 8 cents. So it will just keep doubling. So my question for you is, which of these sounds like the better prize? So if you want, you can go and do some math and crunch some numbers and try to figure out what would be better. We will actually do that together in a moment. So what I would actually prefer you to do is just intuitively make a guess. Which one of these sounds like the better choice? So personally, if I didn't know what I know, I might actually guess the first option because it just sounds better, right? You're getting $1,000 a day. Like that's a lot of money. And it is. And it's guaranteed, right? It's like $1,000, another $1,000, another $1,000. Whereas the second option, it just feels like you're really not going to be getting that much money, right? You get 1 cent, you get 2 cents, you get 4 cents. Like that doesn't compare to getting $1,000 a day. So let's see what actually happens when we crunch these numbers. So I made this table. The way that I labeled the days, I started with 0. So the first day counts as 0. I did that so that when we write down formulas for these two different options, they come out a little bit more cleanly. But yeah, so let's take a look. So if we look at option 1, as we expect, it goes up by $1,000 every day. And so by the time we get to the bottom, we have $31,000, which is great. Would not turn that down. But if we look at the second option, at first, it just really doesn't look that exciting, right? We have 16 cents, 32 cents, 64 cents compared to, $7,000. But if we keep going with it, notice that all of a sudden, it really starts growing quickly and more and more and more quickly. So just to kind of compare, what would be the place where the second option becomes better than the first option? Well, it looks like that happens at 22 days, right? At 21 days, you still have a little bit more with option 1, but at 22 days, you have almost twice as much money by choosing option 2. And then by the end, you would have $31,000 with the first option. The second option, if we put in some commas, we can see that this is over $10 million, which is quite a lot. I probably would not have guessed that if you start with 1 cent, that you would get to $10 million by the end of the month. That's a lot. So what makes these two situations fundamentally different is that one of them is linear growth and the other one is exponential growth. So let's look at kind of comparing how these two different options are changing as time goes on. So for example, if we look at what happens between these 2 days. So how much has the amount in the account increased between these 2 days? Well, it's increased by $1,000, right? Plus $1,000. And then if we compare 2 other days, so let's say we compare day 20 and day 21, well, that still increased by $1,000, right? Because that's how this option worked. This is an option where you just get $1,000 more every day. So let's do the same comparison for the other function, or for the other situation. So if we compare these 2 days, so day 2, or I guess this would really be like day 3 and day 4 because of my numbering system. But if we compare how much the amount in the account has gone up, on this day, it's only gone up by 4 cents. Now, if we look at how much it's gone up from day 21 to day 22, it's actually gone up by more than $10,000. So I'm just going to write plus, I'm going to put that little squiggly symbol to mean about $10,000. So the left and the right-hand column are showing very, very different situations. This left-hand column, the first option, this is a situation where the amount of money is increasing by the same amount every day. And another way of saying this, and I'll write this down on a later page, is that the rate of change is constant, right? We're always increasing the amount by $1,000. Whereas this situation, we're increasing the amount of money by more and more each day. And so in this situation, the rate of change is not constant, right? It's changing. And specifically, the rate of change is getting greater. It's changing more quickly as more money accumulates, right? The more money that's in the account, the more change we'll get because we're just doubling the amount that's in the account. And so this left hand, this option 1, this is a linear function, whereas the one on the right is an exponential function. And so that's really the difference between linear and exponential functions. And again, we'll get more into that on the next page. But I want to tell you the equations for each of these. And actually, for this first one, you should be able to figure it out yourself. So how would we write down a function that represents the amount of money in the account after X days? Well, for the linear one, we could just look at the y-intercept and the slope, right? So what's the y-intercept? Well, we know that at day 0, we have $1,000. And then what's the slope? Well, it keeps going up by 1,000, so the slope is 1,000. So we would have 1,000x plus 1,000. And now this other one, I'm just going to tell you what it is, and then once we have it written down, we can kind of see why it makes sense. So the formula for this one would be 0.01 times 2 to the x. So how can we see that this works? Well, let's try some numbers, right? If we plug in 0 for x, we would have 0.01 times 1, right? Because 2 to the 0 is 1, and that would give us 1 cent. If we plug in 1 for x, we would have 0.01 times 2, and that gives us 0.2. If we plug in 2 for x, we would have 0.01 times 4, which is 4 cents, and so on and so on. And so the reason this formula works is because when we have 2 to the x, that means that we're going to keep multiplying by 2. And that's what we're doing, right? We're trying to double the amount of money in the account. So just to give you a visual on this idea of, how one of them is increasing by the same amount, one of them is increasing by more and more, here are the graphs of the 2 different functions. So this was the linear function. So this was 1,000x plus 1,000. And then this was the exponential one, which we saw was 0.01 times 2 to the x. And so what we can see is that this purple one it's like slow and steady. It's just kind of going up at that same rate the whole time. Whereas the green one, it starts off so low, it almost looks like it's at 0, right? But then once it starts going really quickly to the point where it actually just kind of shoots off of the graph. So we can see that here is the point where the second option becomes the better option. So Again, this is not really unfortunately, this is not a realistic real world situation for most of us, but hopefully this gives you some intuition between what makes an exponential function fundamentally different from a linear function. Okay, so like I said, we're going to get a little bit more into this idea. So as we said on the last page, linear functions have a constant rate of change. And so what that means in the context of modeling, so modeling, by the way, I talked about this in an earlier video, modeling just means using functions to represent real world situations. And the reason we use the word modeling is because it's never a perfect representation, right? The real world is messy. Things aren't going to line up exactly correctly. But so when we're writing these equations, we're kind of creating functions that closely resemble the way that things are going, but not necessarily exactly. Anyway, so linear functions have a constant rate of change. And so what that means is that linear functions can be used to model situations in which a quantity is always increasing at the same rate or decreasing at the same rate. So in which a quantity is increasing or decreasing at a constant rate. Okay, so what would be some examples of situations that can be modeled with linear functions? We saw some of them if you go back to when we were talking about linear functions towards the beginning of the quarter. We saw a bunch of examples in that video. But one example would be the distance traveled by a person or an object. That's only true if you're traveling at a constant speed. So if you are, on cruise control in your car and you're always going 50 miles an hour, if you make a function representing how far you've traveled as time goes on, it will be a linear function. Another example would be the cost of buying a certain number of options. So if you have, for example, if apples cost $2 each, you can write a function representing the cost of buying X apples, and that will be a linear function. So I should say if each item costs the same amount. Okay, so those are just a couple of examples of things that could be modeled using linear functions. So exponential functions, on the other hand, they do not have a constant rate of change. And so instead, the way that their rate of change works is that they're going to change more quickly when the quantity is greater, right? That's what we saw in this example. The more money was in the account, the more quickly that money increased. And so we'll see examples in this video where we have things that are both increasing or decreasing. And so I'm not going to use the word increasing, but we can talk about just change, right? That it's going to be changing more when there's a greater quantity. So exponential functions can be used to model. So while I'm writing this down, you can think about what would be maybe some examples of real world situations that behave this way. Exponential functions can be used to model situations in which a quantity changes more quickly when the quantity is greater. Okay, so what are some examples of situations that can be modeled with exponential functions? Well, the one that I think is maybe the first one that comes to my mind is population growth. So why is population growth exponential? Well, the more, people or animals or whatever it is, your bacteria you're talking about, there is, the more there are that are reproducing. And so the more quickly the population is going to grow. Another example would be if you have money in an account that is earning a particular interest rate. So unfortunately, that doesn't usually look like our previous example where it's doubling. It's not going to be increasing quite as quickly. But if you do have money in an account with an interest rate, because the interest rate is calculated as a percentage of the amount of money you have, the more money you have, the more interest you're going to earn. So we'll see an example of this actually later in this video. Next two are kind of unfortunate ones, but another situation would be the spread of COVID or any virus or any disease really. So, the more cases that are out there, the more people there are that could spread the disease, and so the more quickly it's going to spread, right? So that's why it's so dangerous for diseases to spread, is that the more they spread, the more they will continue to spread. Another unfortunate example is climate change, and I'll show you a graph to kind of demonstrate how we can see climate change as exponential growth. So these situations that I've listed out here, these are all examples of exponential growth. So these are situations where we have an account or an amount that is increasing. Sorry, my screen froze. Increasing exponentially. So that's why it's called exponential growth. The next three we're going to write down are going to be exponential decay. And actually, I guess first I can show you this climate change picture. So this is just from a website called co2levels.org. But knowing what we know about exponential functions, we can see that if you look at the most recent part of the graph, so this is the amount of carbon dioxide in the atmosphere in parts per million, we can see that this part of the graph does not look like a linear function, right? It looks a lot more like an exponential function. And that's not good, right? That means that as the years go on, the amount of CO2 in the atmosphere is increasing at a quicker and quicker rate, which is a lot more troubling than seeing something increase at a linear rate. Okay, a few more examples. So these are now going to be examples of things that are decreasing exponentially. So one thing could be the concentration of a medication or any kind of drug actually, in a person's system. So we'll see an example along these lines later on in this video. But basically the way that it works, if you have a medication or let's say you drink like a caffeinated beverage or an alcoholic beverage, the amount of that substance in your system is going to drop more quickly at the beginning and then start to slow down. And so exponential decay, which is what we'll call these situations where we have, instead of things increasing but decreasing exponentially, they'll actually decrease quickly at the beginning and then kind of slow down. So it still comes back to this idea that when you have a greater amount, it's going to change more quickly. So if you have something that's decreasing, if you're starting with a lot of it, it's going to decrease really quickly at the beginning, but then that decreasing is going to slow down. Another example would be the temperature of a cooling object. So for example, if you have like a bowl of soup or something like that, or you take a cake out of the oven and you put it at room temperature, its temperature is going to decrease a lot more quickly at the beginning. And then as the temperature gets lower, the rate of change of the temperature is going to become slower. Another example would be the amount of a radioactive material. So if you have a radioactive material, the radioactivity is going to decrease sharply at the beginning, and then it's going to decrease really, really slowly as time goes on. So these three examples, as I mentioned, these are what are called exponential decay. Okay, so this has all just been kind of setting the scene. Now we're going to get into a special formula that we're going to use to represent different examples of exponential growth and exponential decay. Okay, so as I wrote down here, there are many different ways that you can use exponential functions to model real-world situations. So this is what I was getting at in the beginning of the video. If you look in the book, you'll see that there are these special formulas for what's called doubling time or half-life. So that's kind of one approach to modeling things with exponential formulas. In this video, we're going to be focusing on one specific formula, which has to do with using the relative growth rate of a quantity. And so I'll explain what that means in a moment. But I just want to give you a heads up that there are just lots of different ways that you can represent situations using exponential functions. As I said, we just don't have time to get into all the different forms, so I kind of picked one to focus on. Okay, so what is a relative growth rate? So this is actually kind of a difficult concept to explain, I think. And what I would say, and I'm going to do my best to explain it, but this is a topic that I think will make a little bit more sense when you get to calculus. So once you are in Calculus 1, you'll learn about derivatives, and derivatives are a way of measuring what's called the instantaneous rate of change. And so basically the relative growth rate is you figure out how much or at what rate a quantity is changing at a specific moment. And so that is what's called, again, the instantaneous rate of change. Then if you take that rate of change and you compare it to the amount of that thing that you're measuring at that time and see what is the percentage, how would you represent the rate of change as a percentage of the amount, that gives you the relative growth rate. So let me write that down. And then I will say that in these problems that we're going to be doing, you're going to be given the relative growth rate. So you don't necessarily need to 100% understand this explanation in order to be successful in these problems, but I do want to give you some idea of what it means. So basically the relative growth rate means if you measure the rate of change of a quantity at a specific moment. So again, that's this instantaneous idea. So if you are somehow able to measure at this moment, how much is this thing changing? If you then take that rate of change and you compare it, and actually I'll say it this way, if you express that rate of change as a percentage of the quantity at that same specific moment, that percentage is what's called the relative growth rate. So again, I know that's a lot. It's probably a little confusing to just listen to me say that or read through that. Intuitively, again, it's you're basically comparing how much the amount is changing, the growth rate. You're comparing that to the amount that you have. And when you do a comparison, one way of relaying a comparison is through a percentage. And so the relative growth rate is a percentage telling you how the growth rate compares to the amount. Okay, so now that we know what the relative growth rate means, now we can talk about how we can write down an exponential function using a relative growth rate or decay rate. So I should say that actually, depending on whether we're talking about exponential growth or exponential decay, sometimes it will be a relative growth rate, sometimes it will be a relative decay rate. Okay, so if you have a quantity that is growing or decaying exponentially, then the quantity can be expressed as a function of time in the following form. So this is the formula that we're going to be using in this video in all of our examples. So it's going to be f of t is equal to c, and I'll tell you what c represents in a moment, times e. So e here just is the number e, and so that's always going to be there, to the r. And so this r is going to represent the growth rate, and then t is just your variable. So I know it looks like we have 4 letters here, but only 2 of them are kind of numbers that you're substituting out. The e is going to stay there. It's just the number e, and then t is your variable. So that's going to be there. So let me write down what each of these mean. So c is the initial amount. So, whatever you're measuring, if you're measuring population or, the temperature of something, it's like your starting point. And then what does R represent? R is the relative growth or decay rate. And so there's a couple of things that we have to kind of clarify with this, which is that the growth rate is going to be given to you as a percentage, but you actually need to write it in this formula as a decimal. So R is a percentage represented as a decimal. And don't worry, we'll do examples of this where you'll see what I mean by that. And then the other thing that we need to know is that R is positive if we're looking at exponential growth. I'll say it this way, for exponential growth. And it's going to be negative for exponential decay. And we'll see examples of this, and that I think will help you to see why that's the case, why it has to be negative if we're talking about decay. Okay, so I know this is a lot, but like I said, I think once we do examples, this will become a lot clearer, because when we do these examples, you're literally going to be handed the initial amount and the growth rate. So you don't need to worry about calculating those or anything. You're going to be given those. So all you need to do is remember this formula and just put in that initial amount and that growth rate in the appropriate places. So let's jump into our first example. Okay, so our first example says the population in a particular country has a relative growth rate of 3% per year. The population at the beginning of 2020 is approximately 110 million. So we're going to answer a few different questions about this situation. So first question we want to answer is we want to find a function that models the population t years after 2020. Okay, so all we need to do here is basically figure out what C is and what R is, and then put them into our formula. Okay, so we know that our formula is going to look like this, right? It's going to look like f of t is equal to c e to the rt. So what is C going to be in this situation? Well, C is supposed to be our initial amount, right? And so in this case, our function is representing the population t years after 2020. And so the initial amount should be the population in 2020, right? That's like our starting point. And so what is that initial population? Well, the problem tells us it's 110 million. So that's 110 with 6 zeros. Okay, what about R? So what is R? R is our relative growth rate. And so it tells us it's 3%. And so this is where I was saying you have to write that as a decimal. So you would not get the correct answer if you wrote 3. That would be wrong. So instead we have to represent 3% as a decimal. So remember that percentage represents something out of 100, right? 100% is 100 out of 100, right? It's like everything. 3% is 3 out of 100. So how do you write 3 out of 100 as a decimal? Well, that's 3/100ths, or 0.03. So 100% would be 1, 10% would be 0.1, 1% would be 0.01. So we'll do more practice with this in the later examples, but when you're in doubt, what you can always do is just take your percentage and put it over 100. And you could even just type that into a calculator and see what it gives you as a decimal, and that will tell you what your rate is as a percentage. Okay, so now that we have these values, we can just write our function. So our function is going to be 110 million times e to the 0.03 t. Okay, so next question we want to answer. So now that we have this function that models the population t years after 2020, we can use this to predict the population in any year really, but let's use it to predict the population in the year 2030. Okay, so what do we need to do in order to predict the population in 2030? Well, we just need to plug some value for t into our function, right? And so what is the value of t we want to plug in? Well, 2030 is 10 years after 2020, right? So we want to do f of 10 to represent 10 years after the starting point. And so we have 110 million times e to the 0.03 times 10. And so another way of writing that would be 110 million times e to the, so when we multiply 0.03 times 10, that becomes 0.3. And so if you type this all into your calculator, you should find that it is approximately, so I'm going to round to the nearest person. Since we're talking about people, you can't have, part of a person. You would get 148,484,469 people. So one thing I want to point out is that it might seem like, because our growth rate is this very tiny number, we're putting this 0.03 as part of our exponent, it might seem like our amount would not still increase, but it does, right? We saw that when we plugged in 10, our starting amount was 110,000, and after 10 years, it came out to 148,000 and, some extra. So we'll see in a later example that the only way to have an equation in this form and have it be a decreasing function, so to represent a situation where an amount is decreasing, the only way to make that happen is if the rate is negative. So it doesn't matter how big or small the rate is. What matters is whether it's positive or negative in terms of whether the function is going to increase or decrease. And again, we'll talk more about that in our later example. Okay, one more question I want to ask is we want to predict in what year the population will reach 2 million people. Okay, so what's going on here? Well, in the last question, we were given the year, right? We had 2030, and from that we figured out that t was equal to 10 because we were 10 years after 2020. So in this problem, we were given the year and we were trying to find the population. This third part, instead now we're given the population and we need to find the year. So this is the opposite. Instead of plugging in a value for t and seeing what that gives us as an output, we need to take our function and set it equal to the output and solve for t. So we want to take 2 million, or sorry, I wrote 2 million, my bad. This is supposed to say 200 million. Sorry about that. Sorry if that was confusing. It's like we already knew it was 110 million, so it's not going to go down to 2 million. Okay, so as I was saying, we need to take 200 million and set it equal to our function. Okay, so how do we solve an equation that looks like this? Well, luckily we just learned this, right? We learned how to solve what is called an exponential equation. And so the way that we want to solve an exponential equation is we first want to start by isolating the exponential part. And then once we've isolated the exponential part, we can use logarithms to take that exponent and bring it down. So let's start by dividing both sides by 110,000. So we're going to have 110 million. Okay. So we can simplify this left-hand side. Let's just do that so that this looks a little less crazy. Because both of these numbers have a ton of zeros, we can basically divide both the numerator and denominator by 1,000,000, right? If we divide both by 1,000,000, we'll have 20 over 11. Okay, so how do we proceed from here? Well, this is an example where we want to use logarithms, right? So we want to take ln of both sides. And so what happens on the right-hand side, when you take ln of e to a power, remember that that just simplifies to the power, right? If you wrote ln of e to the 0.03t, you would bring down that 0.03t, and then you would just have ln of e, but ln of e is equal to 1. So I mentioned this as kind of a specific fact that's useful to know. When you're taking ln of e to a power, it's going to reduce to just that power. Okay, so now we're almost done. We're trying to solve for t, so we want to divide both sides by 0.03. And so we're going to get ln of 20 over 11 divided by 0.03 is equal to t. Now, in these problems, we're usually going to want to type into a calculator because we want to get like a real idea of how many years that is. So if you type this into a calculator, you should find that it is about 19.93 years. Now, that's not quite what the question was asking. The question was asking in what year the population will reach 200 million. So remember that we started at the beginning of 2020, right? So at the beginning of 2020. So if 19.93 years have passed, that means that sometime during the year of 2039 is when the population is going to double, right? Towards the end, because it's 19.93 years. So it's going to be towards the end, maybe in like December of 2039 is when the population is going to reach 200 million. Okay, so another few examples. So this next example says you invest $1,000 into an account with an interest rate of 2.5% per year, compounded continuously. So this is something that we didn't really get a chance to talk about. So there's different ways of compounding interest. And I believe that if you want to look more into this, I think this is in section either 4.2 or, I think 4.2 of your book. They talk about interest. But all I want you to know for now is that whenever you see the phrase compounded continuously, that's telling you that you have a relative growth rate. It basically means that at any given moment, the interest is accumulating at 2.5%. So this is pretty similar to the last question, even though the context is different. We're given an initial amount, we're given a relative growth rate. Okay, so the first thing I want to do is I want to find a function that gives the amount of money in your account after t years. Okay, so how do we go about doing this? Well, we want to use that same format we used in the last question, right? We know that f of t is going to be equal to our initial amount times e times the, or e raised to the relative growth rate, and then that's going to be multiplied with t. So in this case, our initial amount is 1,000, right? We started with $1,000. And so for the rate, we need to figure out how to write 2.5% as a decimal. So that would be, if it was 2%, it would be 0.02, right? That would be 2%. So 2.5% is 0.025. And again, if you wanted to, if you were not quite sure how to write this, you could take 2.5 and divide it by 100. One way to remember that, by the way, is that percent literally means per, like for 100. Cent is an abbreviation that talks about 100. So anytime you see percent, it always means that amount over 100, 2.5 over 100. Okay, so let's write our function. So this would be f of t is equal to 1,000. And I know I put the little multiplication symbol. You don't have to when you're multiplying with e. You can just write 1,000 e to the 0.025 t. So that is our function. Okay, so next question I want to answer is how much money will you have after 5 years? So how do we do this one? Well, we just need to plug in some kind of a t value, right, and figure out what the output is. And so specifically, our function tells us, t represents how many years have passed, and so we want to plug in t is equal to 5. So f of 5 would be equal to 1,000 times e to the 0.025 times 5. And so if you plug this all into a calculator, you will find that it is going to be approximately $1,133.15. So after 5 years with this 2.5% rate, you have made a total of $133.15 compared to your original investment. All right, next question is how long will it take you, how many years will it take to double your investment? So we're trying to figure out how long it will take for our amount of money to become not $1,000, but $2,000. So we start with 1,000. We're trying to figure out how long it takes to get to 2,000. And so what that means is that we want to plug in 2,000 for our output, right? So we're going to take 2,000 and set it equal to the right-hand side and then solve for t. And that will tell us how many years have passed. So we have 2,000 is equal to 1,000 times e to the 0.025 t. So just like in the last one, we know that when we're solving an exponential equation, we want to start by isolating the exponent. So we're going to divide both sides by 1,000. So we have 2,000 over 1,000 is equal to e to the 0.25 t. And so this left-hand side is going to simplify to 2. So one thing I just want to quickly point out that I think is kind of interesting is that, again, the left-hand side simplified to just 2. So let's say that we had started with a different amount of money. So let's say that instead of starting with $1,000, let's say you started with $25, right? If you started with $25, the right-hand side of your equation would be 25 times e to the 0.025 t. So let's say that you started with $25 and you're trying to figure out how long it takes for your amount to double. Well, what's double 25? That would be 50. So if you were solving this equation, you would divide both sides by 25 and you would get 2, or I'll write it out, you would get 50 over 25 is equal to e to the 0.0, sorry, my pen is acting up a little bit, t. And the 50 over 25 would still simplify to 2. Sorry, I don't know what's wrong with my pen. There we go. So my point is that regardless of how much money you started with, if the question is how long it would take you to double your money, you're gonna get the same solution either way, right? So this equation on the left is what we ended up with, and I know we're not done solving it, but this is what we ended up with when we started with 1,000 and we're looking to get 2,000. This equation is what we ended up with if we started with 25 and we're trying to get 50. And so these are going to have the same solution. So one thing that's kind of interesting to know about exponential functions and specifically exponential growth or decay is that it doesn't actually matter how much you started with at the beginning. If you're trying to figure out how long it will take to get double or half an amount, it's going to take the same amount of time regardless of how much you started with. So kind of an interesting fact to know. I'm actually going to erase this because I think if anyone doesn't watch the video and just reads the notes, they will probably be confused by that. Okay, so from here we just need to take a logarithm of both sides, right? We can take ln of both sides. And we know that when we take ln of the right-hand side, that will simplify to 0.25t. And so that means that t is going to be equal to ln of 2 divided by 0.025. And so if you type this into a calculator, you'll find that that is approximately 28.29 years. Okay, so one more example in this video. So this one is going to be now about exponential decay instead of exponential growth. So this one is about drinking a cup of coffee. So caffeine leaves a human system with a relative decay rate of approximately 12%. And I forgot, you always have to put time units. So it's 12% per hour. So at 10 a.m., after finishing your morning coffee, your system contains 100 milligrams of coffee. So our starting amount is going to be 100 milligrams of coffee. So the first question we want to ask is we want to write a function that gives the amount of caffeine in your system t hours after 10 a.m. Okay, so same format as our last two examples. We'll see that there's one key difference with this one. So this function is going to be, again, in the form f of t is equal to c times e to the rt. So c is our initial amount. So in this case, our initial amount of caffeine is 100 milligrams. And sorry, I realized I wrote something wrong. So here I said 100 milligrams of coffee. I should have said of caffeine. Okay, and so our initial amount is 100. And then what is our rate? So this problem tells us that we have a relative decay rate of approximately 12% per hour. And so 12% as a decimal would be 0.12, or you could do 12 over 100, and that is 0.12. Now remember that when we have exponential decay instead of exponential growth, we need to include a negative sign. And we'll see why that is in a second. So let's write down our function. So we have 100 times e to the negative 0.12 t. Okay, so why is it that we need to have a negative sign if it's decay? So let's think about what the shapes of exponential functions look like. So notice that all of the exponential functions that we're working with in this video have a base of e. And so if you think about what the function e to the x or e to the t looks like, it has a shape like this, right? It goes up from left to right. Now, how do we get a graph with a base of e to, instead of going up from left to right, to go down from left to right? Well, we have to reflect it over the y-axis, right? And how do we reflect over the y-axis? We do that by negating t. And so by applying this negative sign to the growth rate, that ensures that the graph will be reflected over the y-axis. And so instead of looking like exponential growth, the way that I have drawn here, the graph will be a shape of exponential decay. And so that's why you need a negative sign. The negative sign is what flips the shape of the graph to make it look like exponential decay. And so I actually have this one graphed, and we're going to come back to the graph in a little bit. But this is what the function looks like, right? So we see that it starts at 100 and then it goes down as time goes on, and that is because of this negative sign. That's what ensures that the graph will have this shape. Okay, a couple more parts to this. So next question is just asking, similar to the other ones, let's figure out how much caffeine is in your system at noon. Okay, so at noon, what is our time? Well, remember that our starting point was 10 a.m. So 10 a.m. is when you finish your coffee and you had 100 milligrams of caffeine in your system. And so when we're talking about noon, we are talking about 2 hours after 10 a.m. And so what that means is that we need to evaluate our function at a value of 2. So we have 100 times e to the negative 0.12 times 2. And so if you type this into your calculator, you'll find that that is approximately 78.66 milligrams of caffeine. Okay, last question we want to answer, similar to the other ones. I want to know at what time will half of the caffeine be gone from your system. So at what point will you be 1/2 as much caffeinated as you were at the beginning of the day? So similar to the other ones, this is asking kind of the opposite direction, right? Here we're given the amount of caffeine and we need to find the amount of time. So if half of the caffeine is gone from your system, well, that means that instead of having 100 milligrams, right, that was our starting amount, we're going to be now down to 50 milligrams. So we have 50 is equal to 100 times e to the negative 0.12 t. And so if we go about solving this, we're going to start by dividing both sides by 100. So we have 50 over 100 is equal to e to the negative 0.12 t. And so that means we have 1/2 is equal to e to the negative 0.12 t. So just like in the last example, I just want to point this out to you that it doesn't matter how much caffeine you started with. You're going to get the same, like even if you had started with much less or much more caffeine, if you're trying to figure out how long it is till you have half as much left, you're still going to get to this point. And so I think that's kind of interesting. It doesn't matter how much caffeine you drink in the morning, the amount of time it will take for that quantity of caffeine to go down by half is going to be the same, regardless of how much you drink. Okay, so from here, we want to take the ln of both sides, right? So we get ln of 1/2 is equal to, on the right-hand side, the e is going to go away, and we're left with negative 0.12 t. And so our last step is just dividing both sides by negative 0.12 t, or by negative 1.2, sorry. And so if you type this all into a calculator, you might be kind of thrown off here, right? Because you see a negative down here, but remember that ln of 1/2 is actually going to be negative. So how do I know ln of 1/2 is negative? Well, ln of 1/2 is asking what power you have to raise e to get 1/2. And e to a positive power will always give you a number bigger than 1, right? Like e to the 0 is 1 and everything bigger is going to be bigger than 1. So ln of 1/2 is going to be itself negative. So you'll have a negative over a negative. And so your final answer will be positive. And so the answer here is, if you type this into a calculator, approximately 5.78 hours. And so the question is asking us, what time will half of the caffeine be gone from your system? And so that's going to be 10 a.m. plus 5.78 hours, right? And so 5 hours past 10 a.m. would give us 3 p.m. And then 0.78 hours, let's just round, it's going to be about 3:45, right? Because 0.78 is pretty close to 0.75, and that's 3/4 of an hour. So at somewhere around 3:45 to 3:50 p.m. is when you're going to be at 50% of the amount of caffeine that you were at the beginning. So one thing I just want to show you about this graph, and that kind of is just about exponential decay in general, that I think is kind of interesting, is we have a horizontal asymptote at 0, right? And so what that means is that as far as you go into the future, according to this function, the amount of caffeine is actually never going to hit 0. Now, whether that's accurate or not is kind of hard to determine, because by the time that this graph is so close to the x-axis, the amount of caffeine in your system would probably be, you wouldn't even be able to detect it. So it almost doesn't matter whether there is actually 0 caffeine or a very tiny amount. But I just want to kind of point that out because I think that's interesting, and that is something that is true of all exponential decay. If you're modeling something with an exponential function, it's never actually going to equal 0. It's going to get closer and closer to 0, but it's never actually going to reach it. All right, so that is it for this video. And I guess this is our last real video of the quarter. So thank you all for your time.